How does a part that was designed in Germany fit perfectly into a machine built in Japan? It's simple. They speak the same language. Not German, not Japanese, but a universal language for precision engineering. So let's dive into this language of modern manufacturing, geometric dimensioning and tolerancing, or as you probably know it, GD&T. When you look at an engineering drawing like this, you're not just seeing a simple blueprint. You're looking at a language, a very specific rule-based language. Every little symbol, every box, every single number is a critical instruction. It tells a machinist exactly how a part has to be made, and maybe even more importantly, it defines the acceptable limits of its imperfection. And that really gets to the core of the problem GD&T was invented to solve. I mean, when parts have to fit together with microscopic precision, how do you communicate what you need with zero, and I mean zero, room for error? How do you get rid of every last bit of ambiguity? Well, you create a language where every single word has an exact, unchangeable meaning. To learn this language, we've got to start with its most fundamental piece, the core sentence. In the world of GD&T, this is called the feature control frame. So every single geometric tolerance you will ever see on a drawing is tucked inside one of these rectangular boxes. That is the feature control frame. It's the absolute foundation of GD&T. Honestly, if you can learn to read this one box, you can understand the main instruction for pretty much any feature on any print. The absolute best way to look at it is as a simple but really powerful sentence. And just like any sentence, you read it from left to right. Each part of the frame adds a specific piece of info, building on the last one, until you have a complete and totally clear command. Learning to read this sentence is really the key to unlocking any engineering drawing. Okay, so if the feature control frame is our sentence, then what's its grammar? Let's break it down and see how it builds such a precise instruction from just a few simple parts. All right, there are 3 essential parts to every single feature control frame, and they always show up in this order. First, you've got the geometric characteristic. That's kind of like the verb of our sentence. Second is the tolerance zone. Think of this as the modifier, like an adverb. And third, the datum references, which give us the all-important context. Okay, let's start right at the beginning. The very first box holds a symbol. This is our verb. It tells us the action. It's telling you what kind of control is being applied. Are we talking about flatness, position, the angle? This one symbol defines the entire requirement. In this example, the crosshair symbol means we are controlling position. So now we know what we're controlling. The second part defines the tolerance zone. It answers the question, okay, but how much can it vary? It specifies the shape and the size of that zone of acceptable error. Here, we see a diameter symbol and a value, which creates a tiny little cylindrical zone. This is our modifier. It tells us exactly how perfect the position has to be. And that brings us to the last and maybe most critical piece of the puzzle. The final sections of the frame have letters A, B, and C. These are the datum references. They give us the context. They answer the question, controlled relative to what? Datums are these perfect points, lines, and planes that we anchor our measurements to. Without them, the instruction is basically meaningless. All right, so we've got the grammar down. Now it's time to build our vocabulary. There are 14 main geometric symbols in GD&T, and they're all neatly grouped into 5 categories based on what they do. The first group is form tolerances. Now, these are really unique because they control the shape of a feature all by itself without relating it to anything else on the part. They're completely self-referential. Is a surface actually flat? Is an edge really straight? That's what form tolerances are for. So here they are. You've got straightness for lines and flatness for surfaces. Then there's circularity. You'll also hear it called roundness, which just checks a single 2D slice of a feature. But cylindricity, that's the real powerhouse of this group. It's a 3D control that checks the entire surface of a cylinder for roundness, straightness, and taper, all at the same time. Okay, let's move on to the next category. Orientation tolerances control a feature's angle, but with one critical difference from form. They must be related to a datum. You can't just be parallel. You have to be parallel to something. The datum is the anchor. The 3 symbols here are pretty straightforward. Parallelism locks a feature at 0 degrees to its datum. Perpendicularity, which you might hear called squareness, locks it at a perfect 90 degrees. And angularity takes care of every other specific angle you might need. It's all about locking in that angle. And now we get to some of the most common and powerful symbols in all of GD&T, location tolerances. These don't just control the angle of a feature, they control its exact, precise position in 3D space, and it's always relative to its datums. By far, the most common one is position, which defines a theoretically perfect spot and then controls how far the real feature is allowed to stray from it. Concentricity makes sure two round features share the same central axis, and symmetry does pretty much the same job but for non-round features that are balanced across a central plane. Our last two categories are the ones that handle the really complex stuff. Profile tolerances are super versatile for controlling unusual shapes or freeform surfaces, while runout tolerances are specifically designed to control errors on parts that spin. So profile of a line controls a 2D slice, while profile of a surface controls the whole 3D form. And it's a similar idea with runout. Regular runout checks the variation in just one circular slice as a part spins. But total runout, that controls the variation of the entire surface as it rotates. So as you can imagine, total runout is a much, much stricter control. So we've gone over the grammar and the core vocabulary, but let's just pull back for a second and ask the big question. Why does this complex language even exist? Why is it so incredibly important? This quote from the National Institute of Standards and Technology really says it all. It's a language to communicate acceptable variation. See, in the real world, nothing can be made perfectly. GD&T gives designers a precise tool to define exactly how imperfect a part is allowed to be while still doing its job and doing it flawlessly. And that has huge, real-world consequences. It makes sure that when parts from all over the world finally come together, they actually fit. It gets rid of ambiguity, so a drawing means the exact same thing in Ohio as it does in Osaka. That universal standard ultimately leads to better products at a lower cost because you're not wasting money scrapping good parts just because of a miscommunication. In the end, GD&T really isn't just a bunch of symbols on a page. It's the invisible language that makes the precision of our entire modern world possible, allowing these incredibly complex ideas to become reliable physical reality. So the only question left is, now that you can start to read it, what are you going to build with it?